Hi everyone. So in this video, we will check the converters required for the making a motor drives. So the configuration of the power electronics converter depends on a factor which is number one is the source available. So what kind of a source is available, whether it is a DC source or AC source. So depending on this, and then the types of the motor. So which type of the motor needs to be controlled. So again, the DC drive or the AC drives, which drive which we need to control, and the drive performance applications. For let's say that we need a continuous duty cycle or intermittent duty cycle. So which kind of a duty cycle is required? All these duty cycle like continuous and intermittent will discuss in the separate video. So depending on these three requirement, power electronics converter depends on which kind of a configurations we need to develop or deploy. So under the drive performance application, one is the braking, that uh, if we need a braking in only the forward direction or also in the reverse direction. So again, which kind of a what kind of application we require for the braking. The response time also, what is the response time is required, whether it is a fast responsive system or the moderate responsive system, and the drives rating. It also depends on that the rating in terms of the kilowatt also decide that which kind of a converter can be handy to deploy. So in the DC drive, if we have the AC source available, which we know that the AC source is easily available to us, which is coming from the grid. So to control the DC drives, we have two options. One is converting directly from AC to DC just by one conversion, and the other one is that first we need to convert the AC into DC, and then that DC to have the better control on the output, we have the one more conversion system. So this one is only using the rectifiers. This is using the rectifier plus choppers. So here conversion from AC to DC. So this is the AC symbol, and here it shows that output will be a DC. And similarly, if we are using the two converters, so this is the rectifier coupled with my capacitor, or I can say the filter, because I need to, whatever DC is coming over here, I need to make it a ripple free, which goes to the input as this chopper, which again converts into fixed DC to variable DC to have a better DC control over here. So for the rectification purpose, for this, the control can be done in the two categories. One in the if we have the single phase drive or if we have the three phase drive. So most of the industrial application uses the three phase drive system, and this again can be of two types. The converter can be of two types. One is the controlled one, which is again made from thyristor, IGBT or MOSFET. Whereas if we have the uncontrolled rectifier, that which is being made from your diode. So very obviously I need to use the controlled converters, which is being made from these three kind of power electronics devices. Whereas for the two-stage conversion, this rectification can be done by using the uncontrolled rectifier. So this is being made from my uh, diode, which on which we don't have any control, because we don't have any gate circuitry or the firing control over the diode rectification. Again, it can be of two types, of the single phase and three phase, depending on my drive requirement. And here we have the DC, which is uncontrolled, and this uncontrolled DC can be controlled over here on at the output by using my chopper circuitry, which is being made from again the control power electronics devices like thyristor, IGBT and MOSFET. So here just showing a kind of a circuit example over here, that for the single phase rectification, the output voltage is nothing but the 2 Vm upon pi cos alpha. So this is the first one where the conversion is happening from AC to DC through the controlled rectifiers, which is being made from your thyristors. And here we have the drive which we need to control it. And here the alpha is nothing but my firing angle. This is nothing but my firing angle. And this is a kind of a waveform which is being shown over here. So red line shows my uh, AC, input AC, single phase in AC waveform, and the blue line shows my output voltage V0, and this is for nothing but for the RL load. So my motor is shown by my RL load over here. Similarly, for three phase converter, we have the output voltage is 3 line to line maximum divided by pi and cos alpha. Again, this, the red line, dotted line shows the three phase waveform, whereas the blue one shows the output voltage DC V0. The AC to DC type which we are talking as of now, as already we have seen the four quadrant operation. So this is nothing but the rectifier, and this is nothing but again working as an inverter. So I'm taking the three-phase supply input over here, which converts into DC. Here at this terminal we have the DC, so I can control the disk drive, my DC drive. However, if I need a regenerative braking, so during the reverse operation or during the braking operation, this machine should work as the generator, so that it will convert my mechanical input, which is here mechanical input. Let's say that my vehicle is going towards a downward motion, and I need to apply a brake, so that kinetic energy can be converted into again the electrical energy, which can fetch back to my uh, either to my storage, battery storage, which is available in um, my vehicle, or else it can feed back to grid. Let's say if this is nothing but the grid supply I'm taking in simple industrial application, so here the same supply can be given back to my grid. Similarly, if we'll take the example of the vehicle, so let's say this I'm taking it from battery. In case of the battery, this will not be a three-phase supply, this will be a DC supply. So DC supply needs to be converted into first AC supply, and then it can get converted back to my DC supply if I need to control the DC motor, which happens in the earlier version of my DC vehicle where the DC series motor is being deployed. So here this color shows that we will have, through this rectifier we will have the control over the quadrant 1 and the quadrant 4. Similarly, through this inversion process we will have the control over the quadrant 2 and the quadrant 3. So in the rectification mode, due to this rectification converter, we can have the forward motoring mode, and we can have the reverse mode. Similarly, by inversion we can have the reverse motoring mode, and we can have this is the forward braking, the quadrant 2, and this is the reverse motoring. Similarly, if I'm using only one rectifier, which is converting my AC to DC, or let's say three-phase AC to DC system, here I'm using which is shown over here, F1, F2, R1 and R2. I'm using the banks over here, capacitor banks over here. So in by this case, what I can do, instead of using one more converter which we have seen just now, inverter, instead of that we can control the direction. Let here F1 and F2 color shows that it can give you, or it can give us the control in the quadrant 1 and the quadrant 4. So this is forward motoring, and this is reverse braking. So this can be achieved by F1 and F2. Similarly, the reverse forward braking and the reverse motoring can be achieved by R1 and R2. So the cascade or the block diagram is shown over here, just that how we can control the uh, quadrant operation by F1, F2 and R1, R2. So here it shows that three-phase supply is going to my three-phase rectifier. Here I have taken the feedback. So this feedback is going on, where this is the feedback, which is the value of my uh, direct axis current, and the value over here, this is nothing but the speed feedback is going over here through this solid line, and the speed feedback is coming to this comparator over here. And just by having the uh, ID reference and ID over here, and I can have the controller over here, one more controller to have the armature reversal, just to rotate my rotor in the reverse direction. This can be done by this. So this is F1, F2 over here, this is R1 and R2. So we can control the reverse direction by using this. However, controlling the speed and all those things, we have a separate controller over here. Please be keep this in mind that we are talking about specifically the DC drive. So DC drive is very easy to control because we have separate current for the flux and separate current for the torque control. And as we know that ID, the direct axis current, is capable of controlling my flux, whereas the quadrature axis is able to control my torque. However, there are some drawbacks which we have already discussed. It has the high cost. Here, the drawbacks of the DC motor control only we are talking about. So, of heavy weight. Losses are high due to commutation and brushes because it is the limitation of my DC motors. And due to that, it also requires the regular maintenance. And we always need a converter to convert the AC into DC because the AC source is easily available. Uh, Converter control is costlier and it is having the low efficiency. So I hope now we know that all the limitations and all those converters being used to control the DC drive motors. In the next video, we will see the AC drives and how it can be more efficient than the DC drive control. Thank you.